Welcome, everyone. Greetings. I hope you're all doing well. And today we'll be talking about first order, first degree differential equations. And we'll see a type of first order, first degree differential equations, which is called exact. And we see how we can use MATLAB in telling whether a given differential equation is an exact or not. So let's start by saying what and understanding what's a first order, first degree differential equation. So a first order, first degree equation refers to a specific type of mathematical equation involving a single variable, usually denoted as x or as y, and its derivative or rate of change with respect to another variable, often denoted as x. And now, in simpler terms, it's an equation where you can have an unknown function y and its first derivative y prime, or rate of change in relation to another variable. Most often x can be t, depending on the context. So the general form of differential or first order, general form of a first order first degree equation is usually written as f y prime and here y represents the function involving the value of x, and y prime represents the derivative of y with respect to x. This is often denoted as dy over dx or dy over dt, depending on the context. And then f into x y prime is a function involving x, y, and y prime. Now the equation here, this equation states that this function evaluated at x, y, and y prime equals 0. Now these types of equations are commonly encountered in various fields, including physics, engineering, economics, and biology, especially when describing rates of change and how quantities vary with respect to each other. For instance, we have an equation y prime is equals to 2x, or y prime minus x is equals to 0. These are examples of first order, first degree equation because they involve the function of y and its first derivative with respect to x, and they are of the first degree. That is, no higher powers of derivatives. Now from that, there is what is called exact differential equation. Now these differential equations can be written as a function m into xy dx plus n x xy dy is equals to 0. Such a function or such an equation is said to be exact if there exist a two valued function f x y such that the total differential of f is equal to this equation. That is, the partial derivative of f with respect to x dx plus the partial derivative of f with respect to y dy. It will give you this function. It will give you the same equation. The same equation. Now we can equate the coefficients of dx and dy. And when we equate, we see the partial of f with respect to x is equals to m, equating the coefficient, and of y is equals to n. Now we differentiate these two equations, with respect to y and with respect to x partially. So equation 5.3, this equation, we differentiate it with respect to y. We differentiate this with respect to y, and this one with respect to x. And this is what we have. Now, by the continuity of second order partial derivatives, we know now that this one is the same as this. The second partial derivative of f with respect to y with respect to x is the same as with respect to x with respect to y. It's the same by the continuity of second order partial derivatives. So then it follows that since these two, as we can see, this and this, and by this rule of continuity, then it says that the partial of m with respect to y is equal to partial of n with respect to x, and that's how we can test for an exact differential equation. So by that by that theory, we can jump into a MATLAB and see how we can do that. And actually, it's not complicated. What we just do, given differential equation, we just tell the user to enter the value of m and the value of n. We get the partial of m with respect to y and partial of n with respect to x, and then we check if the two equates. Yeah. So let's jump into a MATLAB. Let me create a live script, or I can just use this one. We get rid of this. So what we do here, I will use something called symbolic toolbox so that you can make use of x and y. Then let's define the function mx and n. So we'll get this from the user. We are getting an input. Enter the function xy. Also for n, let's get an input. So the function, enter that value of n. Now what we need to do here, we'll use differential the function for calculating the derivatives, partial derivatives. So let's have a comment. We want to calculate partial derivatives of m and n with respect to y and x. Respectively. Okay, so let's have dm dy, and we'll make use of this function my. Then we have dn dx. What this function does, we are getting the partial differential equation of partial derivative of m with respect to y, and this one the partial differential of n with respect to x. Then we are storing them in this variable dm dy and dn dx. So then what we need to do, we will need just to check if if this is equal to this. So let's have a comment check if dm over dy is equal to dn over dx. So we just use condition if simplify. We want to simplify this function. The solution we get so that we can see. We want to simplify both of them. Simplify. Now, if that is the case, then we can tell the user that the given differential equation is exact. Else, the given okay. So in the next video we run it